speed of light, why wouldn't the light be moving at 1.9?
Right. That's what we would think, right? But it doesn't. Okay, because if it did, right? If it did do that, then you'd have to change the laws of physics. You'd have to have a different mu naught or a different epsilon naught or something like that, right? The laws of physics would have to change, right? So let's hit the right arrow here. This is impossible. These are the postulates. So basically Einstein says, look, that's ridiculous. It makes more sense to do this. And of course, if you do this, you get to formulas that have been shown to be just true, okay? So the first postulate is that the laws of physics are the same in all inertial frames of reference. What does inertial mean? They ask this by the way, on the IB test. If you're doing the IB test, if you're one of those people working through the IB test, do the whole thing. You know how you're supposed to like pick only like 2 from the last section? No, just do the whole thing. Let's do that whole test. Do every part of it. Okay. This is one of the questions they ask is, what is an inertial frame of reference? Do we know what it means? It means a frame of reference that is not accelerating. Okay, it's moving at a constant velocity with respect to another one. Okay, and I think, do we have that first postulate? Yeah, you might want to write that down. Okay. Another way to say the first postulate is that there's no experiment you can do to ascertain whether you are moving and the stuff around you is not moving, right? So have you ever been at a stoplight and suddenly all the cars start to move forward and you don't move forward and you're like, gee, I'm moving backwards? Yeah? Well, there we've got the Earth. We're looking at the Earth, and most of us say, well, in the Earth frame of reference, you were sitting still and those cars were moving forward. But if you guys were in like deep space or something like that, there's no way you could do, if you saw somebody drifting by, there's no absolute frame of reference. There's no way to say, okay, you are sitting still, I'm moving, right? You could argue that forever, but you'd always be like that comedy sketch in some movie where these people are always arguing and never really, there's no experiment you can do to ascertain whether you're moving, and right? And this is why it's called relativity, because all motion is relative. You're moving relative to me, right? I'm moving relative to you. And the second postulate, I think, is the same as the first postulate. It's just more specific. The speed of light is the same no matter what speed the source or observer is moving. Isn't the speed of light a law of physics? Yeah, so I think it's covered by the first postulate, but that's okay. This is a little more specific. Yes, sir?
I feel like those two are contradicting each other, because you're saying that there's no way to tell that there's a certain reference point, universal reference point.
Uh-huh.
But at the same time, the second one is saying that no matter what speed you're going, the speed of light is the same. So it's saying that speed of light has a universal reference. That doesn't make sense.
Okay, well, imagine that the speed of light, the question is that these seem to be contradictory because the speed of light could be taken as a universal frame of reference, right? I think is what we're saying, right? Imagine if it weren't this way, right? Okay, this person could run into that beam of light. I could be standing here, right? And I could shine my flashlight. Here's my very large flashlight, right? Okay. I could shine my flashlight this way, and you could, if you sat still, you would read the speed of light as being the speed of light. But if you ran at 1/10 the speed of light into the beam, you'd see it at 1.1 the speed of light. Therefore, you could tell you're moving, right? But what really happens is as you run into that beam of light, you see the light going at only the speed of light and exactly the speed of light, no matter how fast you're going. However, the Doppler shift changes. You know you're moving. If you know the frequency of that light, you'd know you're moving with respect to it. But you wouldn't know whether you're moving or whether they're moving, right? Unless you looked at their legs. No, I'm just kidding. Sorry. Okay. So the second postulate, basically the speed of light, in other words, the speed of light is a law of physics, and so it therefore is all the same, right? Okay. The speed of light being 1 over the square root of mu naught epsilon naught. Okay. Okay. Galilean versus relativistic. Yeah, a Galilean transform is the notion that if I run toward this light beam, that it would be if I go a tenth the speed of light this way, that I would see this at 1.1 the speed of light. Right? A relativistic one would be that as I run toward it, I just always see it at the speed of light, which is weird. That's kind of a weird thing, right? Okay. So here's here is the first thing that he derived, and you can derive time dilation, length dilation pretty easily. Mass dilation is as we say, beyond the scope of a high school class. But I think when you get to college, you'll be able to derive it. So here's the notion. And this is, nobody, by the way, builds a clock this way. But Einstein imagines that we have a clock. And we've got a little source. And we've got a little detector, and we have a mirror. And the light goes up, and it goes back. And this distance is d, right? So the total distance traveled by this light is 2d. And the time it takes to click once, or go tick, is, and this is called the proper time, okay, is just twice that distance divided by the speed of light, right? Nobody makes a clock this way, or maybe they do. Maybe this is what, something like atomic clocks or something work on this principle, right? This is called the proper time. Okay, proper time is is basically what happens in the rest frame, right? It's when tick happens at the same place as tock, right? This event happens at the same point in space as this one does, right? It's not moving with respect to us, right? So the proper time for this thing is twice that distance divided by the speed of light, right? Now, if this person flies past us, how the clock works, right? If they fly past us, well, we see the light travel not straight up and straight down, but we see it travel, and apparently this guy looks like he's going faster than the speed of light, aren't they? Well, maybe not. I guess the light traveled a greater distance than the spaceship, yeah? Okay? But they're going pretty fast, aren't they? Okay? If this person flies by and we're standing here on Earth and we see them fly by, and it's always sort of this what is it, a pentagonal shaped spaceship, right? Okay? As they fly by, we see the light travel a longer distance, don't we? Yeah? How fast do we see the light traveling, though? What's the answer to that always? Yeah, we always see the light traveling the speed of light, right? But it travels a longer distance, and if it travels a longer distance, what must be true about the time it takes the clock to tick? Takes a longer time, isn't it? Yeah, yeah. That's, by the way, all the physics is all done. We got to do a little bit of math, right? But this clock ticks at a slower rate, yeah? And it's not just weird clocks that are designed the way nobody designs clocks. It's time itself. Time itself travels slower in a moving frame of reference. Isn't that weird? Yeah. So as you fly by, you age slower. Water drips slower. Your clock ticks slower. Cheese molds more slowly. Life itself evolves and grows. Cells reproduce. Time itself travels at a slower rate in a moving frame of reference. Now, lest you think this is a way to tell you're moving, and whether you're not, the person in that spaceship sees the same thing happen on Earth. He sees this person's clock tick slower. Their cheese mold more slowly. Yes? And the only way to ever check whether one of us is right and one of us is wrong is for one of us to decelerate, stop, accelerate the other way, and come back and check, which relativity does not apply to accelerations, correct? Yeah, yeah? Okay, yeah. Yeah, sure, sure. I mean, if you fly at close to the speed of light, you really are. If you go out, 20 light years and out back, right, you're going to have aged less time than somebody who stayed on Earth. Yeah, pilots that fly, at most of their life, right, are aging just. It's tiny at those speeds, right? But they're going to age slower. They're going to be younger than their twin who stayed on Earth a slight amount, right? But they won't live quite as long because of all the radiation they receive. Yeah. Question.
Moving almost the speed of light. How do you know you're almost moving the speed of light?
Well, you look back and you see the Earth moving away from you at the speed of light, close to.
Then you're just using the Earth as a reference.
Yeah, that's all right. But you have to, if you're going to compare the time rate of travel, you have to have two different frames of reference, right? Yeah. So Earth is one and this person's the other one, right? Yeah. So, okay, so let's do a little bit of math. Let's look at this path, right? So it goes there, and then in the book they show this is L, and this is L, like that. Okay, and then this distance here is D here.